Hello all and welcome back. So in this video, let's continue our discussion of finding complexities of some algorithm which we have done and now find the complexity of Fibonacci number. So let's get started. Now, if I write the code for Fibonacci number, we wrote it something like this. For a number n, we used to first check if it is less than equal to 1, then of course Fibonacci number we used to take as 1. Else we used to return n minus 1 and n minus 2th number, right? So this is the exact code. If I actually explain you in terms of where we find the complexity, this is some k work which we are doing, and then we are calling for two recursion calls, right? So the relation I can write something like this. My t of n is going to be equal to some k work which I am doing plus t of n minus 1 plus t of n minus 2. Now the relation which I have written for my Fibonacci number, and of course that is absolutely right, but there's still a problem. The problem is that up till now we were able to write for smaller problems and then eliminate one of the I would say term which was not t of n. All the other terms used to get eliminated and we were able to actually find what is the time complexity, right? In this particular relation, this unfortunately won't be possible. Now the reason for that is you have to understand that this recurrence relation thing, right? This is something of a tool which I have given you. And just like that, we have number of tools, right? So in some cases, some tool is actually very easily applicable. In other cases, some other tool is applicable. Though this recurrence one is like you can apply in almost everywhere. So using this approach, we might not be able to do that. So let me tell you another approach, which is of course a lot helpful as well. That said, you don't have to think that the last approach was not useful. No, I think we were able to find out so many complexities for all the algorithm which we have done using that tool, and that was so intuitive, right? So I guess I have seen that for 90% of the cases you will be able to find your complexities using that. For this particular case, let us now try to draw the tree of my recursion, right? So let me try to draw it. The recursion tree is going to look something like this. N, it's going to call for n minus 1. Second, and it's going to call for n minus 2. Similarly here, if I also see n minus 3, n minus 4, oh sorry, my bad, n minus 2, and this should be n minus 3. Let me move it and write it properly. Great everyone, so let us see this. This is going to be n minus 2 and this is going to be n minus 3. In a very much similar manner, this is going to call for n minus 3 and this is going to call for n minus 4. And just like that, we can of course make these calls, right? Now my understanding is that each node is doing some k work, right? If I am able to calculate how many number of nodes are there, right? If I am able to somehow calculate how many number of nodes are there, then I think I can do that. K into number of nodes will be my complexities, right? So I will repeat what approach I am actually saying. Each node is calling the lower nodes and just does the constant work k, which we have seen here. Now, if I just count the number of nodes, and each node I know is doing k work, then I can say comfortably that, hey, I feel that total k into number of node work is getting done, right? So now the next thing is how can I count the number of nodes? Here it is pretty easy. So if you will see, pay attention here, it is just reducing by n minus 1 and n minus 2, right? Like this. Now in this left subtree, we will be actually going till vol n, but this part of this tree, right, this will not be going till vol n. Similarly here as well, this tree is gonna get end first, right? It will not go towards the full end because we are subtracting 2 here and here we are subtracting 1 only. For the sake of simplicity, what I am actually assuming is that, and I will write down the assumption as well. We are assuming that each subtree will, in worst case, end at end depth, or I would say bottommost depth, right? So what I'm assuming is that each of these tree is going to go to the full bottom till 1 and going to take n steps to that. I understand that it is not true. That is some assumption which I'm making to make the work easier. Okay, so this is a very important assumption. Now, if that's the case, let us count the number of trees, number of nodes. In the first, I think there are 1 nodes. Second, there is 2 node, 2 to the power 1. Third, there is 2 to the power 2, 4 nodes. Then there will be 2 to the power 3, 8 nodes. 2 to the power 4, 16 nodes. Like this, my nodes will be there, right? If now that's the case, I can add all of them and get my number of nodes, right? So I will repeat what I have done. I have assumed that each and every of these three, it's gonna actually end at this particular 1 position where we would have made n calls, right? Understood that, yeah, this might end a little bit above, but we are still assuming that everything is gonna get end at same position. If that happens, then if I am able to count the number of nodes, then I can say that, okay, how much time basically is getting done, right? On that note, we have already written, so the number of nodes are 1 plus 2 plus 4 plus 8 plus 16 and all the way till this, right? Now this is actually a geometrical progression. So let's say if I write it 1 plus 2 to the power 0 plus 2 to the power 1 dot 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 till n. If I have to actually now find the total number of nodes, the answer is actually given like this. So 2 to the power 2 into 2 to the power n minus 1 divided by 2 minus 1, right? So this is the sum of GP, something which we have studied, sum of GP, right? These are the number of nodes. If I just write it down, so the total work which I have is k into number of nodes. Now number of nodes we have very fabulously calculated, and it's going to be 2 into 2 to the power n plus 1. Oh, sorry, my bad. 2 to the power n minus 1, right? This finally becomes 2 into n plus 1 k minus 2k, right? In front of this particular thing, okay, of course, this is having no values. This is actually negligible in front of this. So let me just cancel it out. What I'm saying is this constant is not having any significance in front of this particular value. And now what I can write is final Tn I can write as k into 2 to the power n plus 1, right? This I can write 2k into 2 to the power n plus 1, which finally I can write is less than my, let's say 3k 2 to the power n, right? It is not going to be 1. So how can I write this? Because 2 into 2 to the power n is equals to 2 to the power n plus 1, right? If that's the case, then I think we got a complexity. So the complexity is, time complexity is order of 2n. It's horrible, like as horrible as it can. Exponential is like the worst kind of complexity you can ever get. If your code is of the form like this, the one which you have written, it's going to take a lot of time. Okay, it's even bad than n square. We say that it is exponential. It is exponential. Now one thing to note here, it's not going to be completely 2 to the power n. Rather it will be some, there's a golden ratio which is called, the reason is that we have assumed that, okay, all these are going to come towards the end of depth. It is going to be the golden ratio to the power n because normally it ends before, right? So, but that should be fine. For our analysis, we can assume that, and we are getting it exponential. That is fine. So 2 to the power n is very bad. I'm going to help you visualize in the next video how bad is it. But if you have written this code, okay, and for example, say I try to find out 50th Fibonacci number, okay, via this code, it's gonna take a lot of time, a hell lot of time, okay. Maybe we can calculate it faster than the code which you have written, okay. So yeah, that is something which we have to understand, that this is pretty bad in terms of complexity, okay. So I hope you understood the whole process, how we have done this. This is a little different process than what we have seen, though that one is actually very intuitive and will be helpful to us in most of the cases. But yeah, this is again one case where it fails and we have to now resort to other process, okay. Though our aim is always the same, that we are anyhow able to calculate our time complexity, how much our algorithm is taking, okay. Cool then everyone, I hope this approach is clear. Please make sure that you understand that, and also now practice on all the code which we have written as part of our recursion and find the complexities of them, because it's going to be a lot helpful, okay. Cool then everyone, let's meet in the next video. Thank you.